to get going, first of all, you do have your exams returned. Exam scores on here arranged anywhere from 16 up to 100. Excuse me, please. What I would like to tell you about the scores here is this. First of all, I don't know what Professor Roslet does, and I don't care what anybody else of my colleagues do. Here's what I do. When I return exams, I don't go through them in class, in part because I know that some people did really well, some people didn't. And for those that didn't do well at all, spending a few minutes here going through the answers isn't going to do anything for you. And those that did really well, we're wasting your time. I can take more time for those of you that really want to go through their exams with me if you stop by my office, and I can do it one-on-one with you so we can look at your individual problems here on your specific things that you want to look at. So that's how I handle it. Now, as far as the scores go on the exam, if you look at the front page, you're going to see a set of numbers. Here's what those numbers mean. First of all, there's a score out of 18 points. That is the score that you received on the multiple choice portion of the exam. I took the Scantron score multiplied by 3 because they were worth 3 points apiece. Then took that score out of 18 points. Then there's another score out of 82. That is a score that is on the handwritten portion of the exam. To arrive at that number, you're going to see a number in the lower right-hand corner of the front page. That number was subtracted from 82 to arrive at the score out of 82 points. I then sum those two values together to get a score out of 100. That number that's on the lower right-hand corner of the front page is the total number that were marked wrong on all of the handwritten portions. So you can go through and sum the numbers in the bottom corners on pages 2, 3, and 4. You sum together the numbers on the bottoms of page 2, 3, and 4. They should give you the number that is in the lower right-hand corner of the front page. Again, that number was subtracted from 82. So then there's a score out of 100 points that is provided. Now, this is nothing about today is meant to be a lecture to you or at you or anything else. It's just something that I always tell all of my students, and I haven't had a chance to have this conversation with you because this is the first exam that I administered to you, but it is one that I normally have earlier in the semester if I were to have you the whole semester. And that is, read the text. That should be obvious. If you want to know what you're supposed to be reading, I passed out a syllabus supplement on Thursday, exam day. Anybody not get a copy of the syllabus supplement? Okay. Anybody else not get one? So let's pull that out and look at it here very quickly. Anybody else needs one? Anybody else? All right, if you look at the syllabus supplements, here's the information that you can get out of that syllabus supplement. And I don't remember if I have that up here yet. Here we go. So on there is a reminder of what my office hours are. Then I do have the modified lecture and exam schedule from this point forward in the course. I did tell you the very first day that I walked in here and met you, which by the way scared the crap out of me. But I did tell you on that first day that if I were to become your permanent instructor from this point forward, that I would have a proposed change on the syllabus, and here it is. Exam 4, I believe, does show up on your syllabus as either the 20th or the 18th. I have moved that to April 25th, and that is going to cover chapters 7 through 9. If there was just an exam on chapters 7 and 8, there would not be enough material to cover for a given exam. So if you go on to the next page, this is your study guide, so to speak. These are the things that you should be studying or practicing. These are the problems that appear at the end of the chapter, and these are the ones that I suggest you do at a minimum. Again, this is at a minimum, not at a maximum, but at a minimum. because this is basically one of each problem type. And if you are good at something by doing something one time, then this is all you need to do. But if you're somebody that needs to do something more than once, then you should be doing more than what is listed on here. Now this is for the textbook that was sold in the bookstore. That is this one right here. If you are using an old textbook that was used previous to this academic year, and I understand also that Professor Rosselette had accidentally selected the wrong textbook the first time he made the Mastering Chemistry course, and some of you may have enrolled in that course, which not may have. I see that about half of the class did do that. If you did, and end up purchasing the e-text is actually to the 3rd edition, and these are the problems that correlate with that 3rd edition of the textbook. So if you're unsure which edition you have, just let me know what it is you have, and I will come up with an alternative problem set, or you can make a photocopy or whatever of someone who does have them. What I have done then is I've gone into Mastering Chemistry, and these should now all be visible to you. I've gone in and set up what I call practice problems and homework assignments or homework quizzes. A homework assignment or homework quiz, same thing. I've always called them homework quizzes, but I didn't want to confuse some of you, but I probably did because I might see I left quiz there and this one doesn't say quiz. Anything in red here is the same thing. These are the things you'll find on MC, which stands for Mastering Chemistry. So Mastering Chemistry Chapter 7, 8, 9, and 10 we have the due dates for. The practice problems. These are ones that are identical to these problems here. So the ones that are listed here as practice problems, those are identical to these here, and I have selected them and placed these into Mastering Chemistry as well. And if you've been in there, these under Mastering Chemistry will earn you some extra credit. Exactly. It'll be half a point extra credit for each one that you complete with a score of 80% or above. And that's just so you don't just do a little bit. You should really be doing all of them anyhow to practice. But this way, if you practice them, you'll get some extra credit if you do them here on Mastering Chemistry. Now, I guess we'll kind of take that where it is. Any questions on the assignment pieces? Yes, sir.
As far as Mastering Chemistry goes, I noticed when I pulled up chapters 7, 8, and 9,
yes,
the points are out of like 82, 99, and 101.
Okay.
Whereas previous ones were 8 points, 12 points.
Yes. Here's what those things mean. If I look at your syllabus, and by the way, I just want to reaffirm with you that I plan to stick, the only change I've made to your syllabus is exam 4. Otherwise, I plan to stick to the entire conditions that I've read as a part of your syllabus, which means out of 4 exams, you have to take 3 of them. And if you wind up taking all 4, that means your lowest score gets dropped. So I plan to abide by all of that. The final is not one of those. That's in your final. If you read it is worth 200 points in there, and I will stick with that piece on there as well. But as far as the Mastering Chemistry goes, what I read on there is that each one will be normalized 10 points. And so, if it says 89, and you get 95%, then that will show up in D12 as 9.5. Okay? So that's how that all works. And the reason why I do it that way is so when you look at them, if it's the Mastering Chem, the ones that are in red up there, when you go to do your homework, I set those point totals for each question that's equal to the number of minutes it took on the average for students to complete that problem nationwide. So if a question is worth 23 points, that means that I looked up the statistics for that problem on a national basis, and it took 23 minutes for your peers nationwide to complete that problem. And so I basically weighted them based on the amount of time that it would take you to complete each one. But in the end, then that total score will be normalized to 10 points as per your syllabus. Okay, anybody else? And if you see it's worth 89 points, then it's going to take you on the average 89 minutes. Yes, sir. Yes, you may. Anybody else with a question? All right, then our final exam in here is going to be on Thursday, May 11th. It will run from 11:50 to 1:50. It'll be in this room. We'll be using the period here on Thursday, May 4th to review for that exam. But prior to that, after exam 4, I'm hoping I do like I did this time. I get our exams graded by the next class period. I won't promise. I'll do my best though. On this day, I will have a guide for you that will talk about how to prepare for that final exam. And for those that do wish to do some preparation, the not the bookstore, well, maybe the bookstore will. I know for sure the library sells a guide to the ACS exam, not sells. I'm getting us all confused. The library doesn't sell, right? The library checks them out, all right? And so you can go down to the library and they'll have like a review guide for the ACS final in there. When you look at it, you're gonna say, I don't know some of this stuff. That's because it's for a full year final. But if you look at the pieces of things like gas laws and thermochemistry and stuff that we covered in there, you can then find the appropriate questions that pertain to the first semester. And then I know in the past the bookstore has sold them, but if you look online for the ACS General Chemistry Final study guide, you can look it up and you'll probably even find it on eBay for all I know. So with that, tips, studying. We talked about reading the text, doing your suggested end of chapter problems, doing your mastering chemistry homework quizzes. I might write the most beautiful work up here and you might say, wow, I understood it when I was in class. Well, it'd be just like the basketball coach that throws the most beautiful free throws. If you're watching me throw free throws, what does that do for you? Nothing, okay? If you listen to me play a beautiful piece of music, what does that do for you? Nothing. You have to practice the stuff. I can't do the practicing for you. So you need to take that on. And so what I just always remind, and again, this is not a lecture at you or to you or anything, something I always do with my students when I meet them after the first exam in my other classes. Visit me during office hours. See the tutors. We have a whole slate of peer tutors, professional tutors, online tutors. They're all free. The online tutoring is 24/7. And I have a link to that on the main course page of our D2L course. And so you'll see there's a link to Smart Thinking Tutoring. If you click on there, all Anoka Ramsey students have 15 free hours of tutoring through smartthinking.com. Study groups. If you've not yet done so, forming a study group is a good thing. The professional tutor down there will oversee that. Oversee it in the sense that will provide you a space to have your study group. And then if while you're in there working in your study group and you have questions, then any of the peer tutors or professional tutors that are available in the academic support center at that time are more than happy to help you. But they do like, if you do form one, that you try to have a regular scheduled time. So if you say you want to meet every Tuesday at 11 o'clock, then they will try to set that space aside for you each week. And then as a final reminder here, the last day to withdraw is 2 weeks from today, which is Tuesday the 18th. If you do feel like you're in a position where you're concerned about your status in this course, I don't discuss it on D2L, I don't discuss it in the class here. Come to my office and I will talk it over with you. Any questions that you have? All right, let's get going then on our stuff here for today. You should have picked up one of these diffraction gratings up here, and we also have a handout. Did not get one, come up, you need one of each one of these here today. And what I'd like you to do is to pick up the diffraction grating. And by the way, on that handout, if you look at the images that are on there, your diffraction grating looks something like this. And I need to spell it right. And say diffraction grating. And now there's two sides to your diffraction gratings. One side has a side with the phone numbers. Don't look at that one. You want to look at the side that has the numbers on the bottom. They go from 300 up to 700. Now, if you look at the very top of that side, it tells you how many lines are on there. It says that there's how many lines per millimeter. It's 1,000. And so if you know that there's about 25 millimeters in an inch, that means in every inch there should be how many lines approximately? Right, so we have about 25,000 lines per inch that are on here. Now, of course, if you try to look at those lines, why do you think you can't see them?
Too small.
They're too small, exactly. So what I'd like you to do, though, and some of you already discovered it because I see you doing this right now, go ahead and put it up next to your eye and look at the lights in here. And you're going to start, and I'll keep the number scale on the bottom, so the 300 to 700, keep that on the bottom. And what do you see when you look up at the lights? You noticing anything?
Different colors.
Yeah, you're going to see the rainbow of colors. And so we're not going to talk about the physics of how that happens, but there's a reason why putting these lines on here will do that. But you've probably noticed the same phenomenon before if you've taken a CD, which I know maybe people don't even know what those are anymore. But you could take a CD or you can take a DVD. If you hold it up to the sunlight, you're going to see the same thing. You're going to see a kind of rainbow of color. And the reason why you see that is because on that surface there's a whole bunch of very closely spaced lines that are on there. And the process that the way the light is interacting with the lines on that surface is through the process of diffraction, which is the same thing as happening with these diffraction gratings here. But what I'm going to do here now is I'm going to take this light bulb, and this is an incandescent light. I'm going to plug this in, and this is probably where we're going to need to close the shades over there. So we're going to do some stuff in the dark here real soon. It's not quite as dark as it's going to be here in just a bit. So I have some others that we're going to look at. But once again, take your diffraction grating, make sure that the numbers are at the bottom, bring it up to your eye, and now look at and now turn your head from left to right. Rotate it back and forth. And on the one side, you're going to see the colors in order from red, orange, yellow, green, blue, violet, to the other side where it's going to go violet, blue, green, etc. So again, if you rotate to the left, you're going to see them from red to violet. If you rotate to the right, you're going to see it from violet to red. We're going to want to focus on the one that goes from red to violet. And if you look at that color from red to violet, anybody know your mnemonic? Roy G. Biv, exactly. And what Roy G. Biv stands for is red, orange, yellow, green, blue, and what is this? Indigo and violet. And I just put the indigo in there to help us with the mnemonic in there. So Roy G. Biv tells us the colors of the spectrum. Now when you learn them in that order, what you're actually learning is the colors of the spectrum in order from low energy up to high energy. From low energy up to high energy. And I see now that apparently when I copied and pasted this over, all of my reveals are now revealed. You were supposed to guess these, but now they're all up here for you. What you're seeing up here is the other portions of the electromagnetic spectrum. And so you might as well write them in, because I don't know what happened when I copied and pasted this. It didn't look this way in the morning class, so I must have pasted yours differently than I pasted theirs. But if you can't see this, down here we have radio waves, we got microwaves, we have infrared radiation, we have ultraviolet radiation, we have X-rays, and we have gamma rays. And I'm going to turn the lights back on here for a bit. They're going to go off in a bit again. But now when we look at these, you'll see that visible light actually comprises a very small sliver of the electromagnetic spectrum. And to the right of visible light sits these forms of radiation, which we refer to as being ionizing forms of radiation. So this here, to the right of the visible light, is what we call ionizing radiation. And the stuff that sits here to the left of the visible light, this is stuff that we refer to as non-ionizing radiation. Now, since I haven't been with you all semester, I don't know what you've covered or not covered for vocabulary, but I imagine you talked about ionizing. What does it mean if you ionize something?
You remove or add an electron?
Right, it means if you add or remove electrons. And so when you add or remove electrons, then you form particles called ions. So ions are charged atoms. And so these forms of radiation here are all capable of causing ions to form. And we can also talk about these as forms of penetrating radiation. And they have different levels of penetration. For example, if we talked about ultraviolet light, what is another name for ultraviolet? We call it UV, right? And what does ultraviolet radiation cause? Sunburn or suntan. And if exposed for it over a period of many years, you wind up with skin cancer, right? But this here, we talk about it in which part of the body? Which part does this affect? I mean, it affects the entire body, but just the outside, right? So this type of radiation is not very penetrating. It penetrates just through a few layers of skin. How about X-rays? This penetrates the whole body, right? And if we go to gamma rays, this is the most penetrating yet. This stuff here will penetrate through a few inches of lead or several feet of concrete. And so the further we go down this direction here, when we talk about it being high energy, we increase its penetrating capability. And all of them are associated with different forms of cancers if we have longer term exposure to it. And part of the reason why they have the ability to cause cancer, when we say that they are ionizing, you might go back to something like DNA. Now, this isn't a biology class, but if you've had some biology before, you've probably talked about the structure of DNA a bit, and it's described as being a double spiral helix, okay? And that double spiral helix, it's a long molecule. They have these strands that come up along there, and part of what holds them together is things called hydrogen bonds. The hydrogen bonds are something that we don't discuss in this class, I think, at all. It's probably the first semester in Chem 2, or the first week in Chem 2. But in there, you'll talk about how hydrogen bonds are affected by such things as charges. And so if you go back to some of your early study in this course, perhaps one of the things you talked about was how charged particles interact with each other. For example, if we have two particles that have opposite charges, opposites will attract each other. If they have like charges will repel each other. So when substances absorb some ionizing radiation, what will happen is that it will cause ions to form. If we're talking about something like DNA, which is a very long, complex molecule, let's say that it kicks out an electron in this part here, and there's two parts of these strands that were intended to attract together. Well, all of a sudden, kicking out an electron causes this to be negative, and it's attracted to something else that was negative. All of a sudden, then, instead of something that was originally attracting, is now then repelling. Or it could kick out and cause something that was originally repelling and then cause it to attract. And so that's why ionizing radiation isn't good, because if all of a sudden then you have something that's attracting where it isn't supposed to, or it's repelling where it isn't supposed to, then all of a sudden this DNA, which replicates itself when cells multiply, can replicate that error when it does so, and then you wind up having cells that can multiply rapidly out of control. And so that's stuff here that's caused by the ionizing forms of radiation. If we go over to here, this is non-ionizing forms of radiation. As far as how they affect things, you may not know about all of these here, but I think most of us know about this one here. What do we use microwaves for? What else do we use them for? Use them for eating food, right? In fact, all of these over here, all of these forms are associated with heat. They're in one way or another. Infrared is like what you feel in the toaster, or it's what you feel right here. The heat that's coming off of here is due to the fact that this bulb is giving off infrared radiation, and my hand is absorbing that infrared radiation and feeling warm. Now, how many are military, ex-military in here? Okay. Marines probably do this. night vision. Okay, and what does night vision use?
I don't know.
You don't know which one?
What it uses.
Oh.
I know how it looks.
Yeah, you know how it looks, but it's this one right here. It
Yeah.
uses infrared radiation. And when you use the night vision, what are you seeking? What do you see?
Heat signatures.
Heat signatures. Those heat signatures actually come from the infrared radiation that people are giving off. Okay, so basically it takes that infrared radiation and it turns it into things that you can see, which most night vision, I've not worn them recently, but I think most of them is just either light or dark, right?
Yeah.
Or
They can. You can really see what it is.
Yeah. But now, like, if I wanted to do an energy audit with my house, they would then do a thermal image of my house and look for where heat is leaking, and then they can actually colorize that, and so you can actually see different shades of colors represent different amounts of heat. Usually we use like red or whatever to represent areas that are really hot, and then kind of blue and violet colors to represent cold. So sometimes it is translated into color as well. But in terms of what happens when substances absorb non-ionizing radiation, in this case we're not kicking out electrons, but rather what happens is that when molecules absorb this radiation, they begin to vibrate faster. And as they vibrate faster, what do you think is going to happen to the temperature? Temperature goes up. And that comes from your kinetic molecular theory back with your gas laws, when you talked about the average kinetic energy of the molecules is in direct proportion to its temperature. So again, as those molecules speed up, then the temperatures increase. You mentioned something about spying. Well, we have our cell phones here and everything. And these, by and large, actually operate in the microwave portion of the spectrum. So back when these first were coming out, people were thinking, oh, we're cooking our brains or whatever when we do this, but these have such a low level radiation that most of the research, not 100% conclusive, but most of it seems to suggest that the levels of radiation that these put out are such that they're insignificant. We don't need to worry about what happens with those. But again, these are typically associated with heat energy, because when molecules absorb this type of radiation, molecules start vibrating faster and the temperature goes up. Now, like for you, any questions on that?
Yeah, so like security cameras where they have the small red dots, is that infrared as well, or is that?
Yeah, that's infrared, and it's just basically then you shine infrared on them. Infrared is invisible. In fact, the heat that I feel coming off this is not from the visible light I see, it's actually from the infrared radiation that this thing is giving off. That's not a part of that visible spectrum, but it'll basically shine infrared radiation on you, and then it'll have some sort of detector that will pick up infrared radiation. Okay, and it's similar to the night vision goggles that we mentioned as far as how they're constructed. Any other questions? All right, let's see. We want to make some points about this. Let's go back. We're going to turn the lights down again. Pick it up again so that you have your number scale on the bottom. And I'm going to have you look at the light up here one more time. And I want to show you something kind of cool with this. I'm going to just put my finger in front of here. You see my finger going up and down?
Yeah.
Now, do you know why you can see that so well with the diffraction grating? Well, part of it has to do with the way that this is constructed. This is a filament, and it's a vertical filament. This is not any ordinary incandescent light. Instead of a filament kind of being like it is an ordinary light bulb where it is kind of lays horizontal, this filament in here is vertical, and that's what enables us to see that continuous spectrum. The lines that you're seeing across there right now are actually the brackets that are holding that filament upright in there. And you probably even see, if you look very closely, you can probably even see the filaments in the little coils going up when you look in the diffraction gratings themselves. But now keep that diffraction grating up there, and what I'm going to do here now is I'm going to get it even darker in here, and I'm going to move on next to this device. And this next device, oh turn the light on just up in front of me here. Have a bulb, and this bulb now is one that has been filled with a gas. And it's different than this one. What you're seeing in this one here is a continuous spectrum, and a continuous spectrum is produced by a hot solid. What we're going to do with this one now is that we've placed the gas into each of these. I'm going to show you 4 different ones. We placed the gas in each one. This particular one has hydrogen. The second one that you're going to look at will have some helium in it. Then the third one's going to have mercury vapor, and then I'll let you guess what the fourth one is. But again, we're going to look at hydrogen, helium, mercury vapor, and then a fourth one. And then if you look at it, you're going to see that this appears as it has kind of like a little melted bow off of there, and that's exactly what it is. What we've done is we've placed hydrogen into here, then we hooked it up to a vacuum pump to reduce the pressure, and so the hydrogen that's in here, it sits at a pressure of about 10 to the negative 5th atmospheres. And so I'll put the hydrogen in there, and then the helium is similarly constructed. It's got the little piece melted on here, and I'll put the helium into this one. And I'll turn the lights off, get your diffraction gratings ready. Go ahead and look at this one here first. Make sure you can see the spectrum, and then go ahead and look at the hydrogen one. And now this should look very different than the one you just looked at. And what are you noticing on this one? There's some lines, exactly. There's some lines. If you look at them, what color lines are standing out?
Purple.
Yeah, there's a red one, kind of a purple one. There's kind of a turquoise one, depending upon whether you're colorblind or not. And I apologize, it might appear a little different to you. And if we could get a totally pitch black in here, and it's very difficult, and it's only if you have the most acute vision, you might actually see a second violet line that sits right on the edge of the visible spectrum for us. But with the extra ambient light in here, we probably can't get it dark enough to see that particular one. But again, this one is hydrogen. I'll have you look at this next one. This one here is helium. Now as you look at the helium, does the helium look the same as the hydrogen one? No. Okay. And I will come over here, I'm going to grab the mercury vapor one. And we'll pop the mercury vapor one in. And you'll see that the mercury vapor one, is it the same or different than the other two? Different again. And last one is a mystery one. I will let you guess what this one is. Get it in here, right? This one is?
Neon.
It is neon, exactly. This one here is neon. And now, is this one the same as any of the others? No. But this is my favorite. You see how dark those, or bright those lines are. I'm going to turn the lights on. Again here. Okay, now, here's what it is we're observing with these. First of all, if I come back, and I don't know where my stylus is, must be here somewhere. There's always an emergency one inside of here if I need it, which fell out. Okay, remote controls, just like at home, right? Okay, thank goodness there's always somebody else at home to find the remote, because I never can. All right, so here's what the difference is. The first one we looked at was a continuous spectrum. It's also called the white light spectrum. Okay, so these here are the same thing, and these here are produced by a hot solid. These are produced by a hot solid. And these down here, these are produced by a hot gas. Now there's part of the reason why the incandescent lamp feels hot. And this is one of the things I used to do when I was growing up. I don't know, maybe some of you like to play with fire or whatever, but I used to play around with fire quite a bit, and if I could stick anything with the fire, I did. And one of the things I used to do is I would take like pins or pieces of metal, and I put them into a candle and watch what happens to them. Or I take an iron into a much larger fire. And of course, what will happen if you put a pin in? How many ever done that before? Anyone in here? Yeah. So when it first starts glowing, what color is it glowing? Red. And then it gets a little hotter, and then it turns orange. It gets a little hotter, and it turns yellow. If it gets hotter, it turns, well, now it doesn't turn green, it turns white, or it might melt. So just like this thing up here turned white, the reason why this turns white is because what's happened, first of all, as we're heating something like this, remember, sitting down here is the low energy, sitting up here is the high energy. If you start heating something, say like a piece of metal, the first thing it's going to start giving off, you can't even see it, is going to be infrared radiation. You're going to feel it as heat. But then as you keep expanding this and it gets higher energy, then it starts picking up some of these reds, and then it picks up some of the orange, and then it starts picking up, and pretty soon it starts picking up more and more of the spectrum, and you see that then, or observe it as a white light. But if I put my hand up here or try to grab a hold of it, how do you think this is going to feel? It's going to feel hot. The reason why it feels hot is because we still have some of this infrared radiation that this thing is giving off. Of course, now what we've done is we've taken these lights and we replaced them with lights that are up here. And this one's kind of cool now. If I walk around with these, I don't think I have enough of these for everyone to have one. So if you're sitting next to someone, I think you'll need to share. But I have a couple down here. One, two there, two in this row, two in this row, two in this row.
It's just piece of
I have some more, don't worry. Now please don't push the ends of these. It looks like somebody did that in the morning class. Now, which rows did not get enough for everyone? Yeah, one here. This row here, one in there. You guys get anything? No? Alright, I have an extra here. Okay, you got one down there? Alright. So, here's what these things are. Okay, and they're constructed a little bit differently than what you have out. The way that these are constructed, if you look at them, and please don't poke on the ends of them or anything else, there's two ends. If you have these tubes, one end has like a little diffraction grating in there. That's a grating just like this. You'll see a plastic end. The other side has a small slit in it. Now what you're going to do if you have one like this is you're going to have that slit vertical. You're going to point it at the light, and then you're going to take this piece and you're going to rotate it so you see a spectrum just like you did with these. And if you have these boxes, the diffraction grating sits in the narrow end. There's a slit here on the fat end. Just point that slit up at one of the lights up here. So go ahead and point the slit up at one of the lights. Again, if you have the round ones, you want to rotate it so you can see the vertical lines. Now if you look at those vertical lines, it turns out that those vertical lines in there is going to match one of the 4 gases I had up here. Any idea which gas it is matching? Remember, we looked at 4 of them. We looked at hydrogen, helium, mercury vapor, and neon. So which one do you think that spectrum up here is matching? It's matching mercury vapor. Matching mercury vapor. And that's because these are mercury vapor lights. these fluorescent lights have mercury vapor in them. And part of the reason why they have mercury vapor in them, in fact, the mercury vapor is just like, if you were to focus it on this light here, if you can focus them up here, you're going to see that those lines match this one here. But you might say, well, this one looks kind of like a violet or purple color. That one up there is kind of a white color. Well, what they do with these up here is they coat them with a white powder. And when this then gives off the radiation, it'll give off that radiation, it'll be absorbed by that white powder, and then that white powder will give off a broader spectrum of light. But now, a big difference here is this. If I were to compare energy efficiency between this one and those up here, which one of these is more energy efficient? Those are up here. These here aren't energy efficient because most of the energy goes into producing heat, which of course is actually not so much heat. We perceive it as heat. Again, it's actually which radiation? It's infrared. Okay, so that's why it feels warm here, is because most of the radiation is going into producing infrared, which you and I can't see. Then in the winter, what will happen? That's okay. I mean, especially if we're in Minnesota, this isn't going to waste. But if now we go to summer, this thing's going to give off heat. We pay for that, and then we have to pay for the air conditioning to cool it back down. So then we've gone to those which are more energy efficient.
How about like LEDs?
LEDs. Well, anybody know where you have LEDs? Most of you have LEDs in here. Your phone, right. So this was the first time I did this today, was one of these. And somebody asked, well, what about LEDs? Well, if you want to see what LEDs do, just go ahead and turn on your little flashlight. Go ahead and put your, aim the slit on your light on the LED and examine that spectrum. Okay. And I think what we found out is that the LED is a more broad line spectrum, and I don't know enough about white LEDs. I guess I'm going to have to educate myself. I don't know enough about white LEDs as to why it is broad spectrum. But a lot of LEDs, like if you see a red LED or a blue LED, those are a single wavelength, and you would see a single line in the spectrum if you were to look at one of those. Okay, anybody else? All right. But now, because those are mercury vapor, where can't those things go when they're all done? Can't go in the trash. You got to recycle those things. If you have the little compact fluorescent little curly Q bulbs, those can't go in the trash either. Those are supposed to be recycled because of the mercury that's contained in them. You might say, well, why do we have them in mercury in the first place? Well, it turns out that the amount of energy that these consume over their lifetime are, let's see, the amount of, here's how it goes. If we looked at the amount of mercury that's in coal that would be going into the atmosphere over the life of one of those bulbs, we'd put more mercury into the atmosphere by burning the coal for one of these over the lives of several of these bulbs than we'd put into the atmosphere with just one of those bulbs. So even if that would break, it's still putting less mercury into the atmosphere than the total amount of mercury that would go into the atmosphere by burning coal for an incandescent bulb. But mercury still isn't good, so these then are being replaced with LEDs. And so if I do this in 5 years, we have a plan here at the college, we're getting rid of all the fluorescents, I think within the next year or two. And so I won't be able to do this very demo that we just did in here, because we'll be looking at LEDs to talk about. Okay, any questions? Okay, so now, where does this take us? Well, we are going to be looking at some of the behavior of light, and it turns out that we say that light has a dual nature. And we say that it has a dual nature. That means it has two different sets of properties. We say that primarily, light behaves primarily as a wave. And And so waves all have properties. In fact, what we just looked at, when we looked at the diffraction patterns that were produced, that's actually a wave property. But waves go through things where they go through wave addition, wave cancellation, they go through reflection, refraction, all very predictable properties, and light has all of those. But it turns out that light also has some particle-like properties. And one of the particle-like properties is shown by another figure in your packet. This one here relates to the photoelectric effect. Now, in the photoelectric effect, and this is why we say it behaves like a particle, is that if you look at this calculator, which has a small solar panel on there, what will happen is that when it's exposed to light, light will strike this, but when it strikes this surface, it causes electrons to get kicked out. As long as we keep exposing the light, electrons will keep getting kicked out of here. So eventually, if we keep kicking electrons out continuously, you'll wind up with a flow of electrons, which we call electricity. And there's enough electricity that will flow through here to be able to power the calculator. Yes?
It doesn't work with LEDs.
Doesn't work with LEDs. And I don't know if we say it doesn't work with LEDs, if it's well, we'll find out, I guess, once we get the LED lights in here.
So we have all LEDs at my house, and I'm like,
So white LEDs then, obviously. Yeah. So I guess I didn't know that. So we'll see. That's interesting.
Batteries are bad. Yeah, good calculators.
But now that is surprising, because when we look at our calculations today, it should show that that should still work. So, but it might be just that there's not enough of them that are hitting the surface to cause the current to flow. All right. So basically what will happen then is that, again, it will strike the surface. Once it strikes the surface, the electrons come out, and it's something that you should be able to measure on a voltage meter or amp meter of some sort. And the idea is, when I say it has particle-like properties, basically it has to have some momentum. So if I was walking by one of you and we bumped into each other, if I bumped you, then your path is going to change a little bit. And that's what we say when things have momentum. When something that has momentum, that means it has both mass and speed. If you bump into something else, it should be, cause its speed to change or its direction to change or something else. Its momentum is going to wind up changing. And so that's exactly what happens here again when light strikes the surface. So there was a scientist by the name of Albert Einstein who came up with this idea. And what Einstein had said then is that we can envision light. So Einstein said that light can be envisioned to come in packets or bundles of energy which he called quanta or photons. And according to Einstein then, and we're not going to go into all of the physics of this, but we'll look at the final result. Basically what he found out is that the energy was directly proportional to the frequency in which those particles struck that surface. Now, I heard from the morning class that you had not seen this symbol before. Okay? This symbol, when you write it like this, stands for is proportional to, or is directly proportional to, exactly. So what that means, if we were to double the frequency, we would double the energy. That's what this means. So now we need to have some symbols. We're going to be doing a number of calculations. That's kind of how we're going to wrap up the hour here today. And do some calculations that involve some of these different problems that you'll see on in your packet. First one here, and I guess is one more definition. We have to define wavelength. We define wavelength. We define as being a distance from peak to peak, or from trough to trough, or basically two identical points from neighboring waves. And so this here represents the wavelength. And wavelengths, we have assigned a new variable which we label with the letter. Anybody know that? Try to write it better. Anybody know what Greek letter that is? It's a lowercase lambda. Okay, so kind of looks like this one here. It's the best I can draw. That's how mine are going to look. All right. So that is the wavelength, and we designate it by the letter lambda. The frequency, if we go back to this one here, the frequency is going to be designated by this Greek letter, which is kind of looks like a little slanted or italicized V with a little arm off this. This is the Greek letter nu. It's lowercase nu. And nu is used for frequency. So if you were to read this in the text, it would look like this. It would say that the energy is directly proportional to nu. So now that we have these two variables, again, lambda is your wavelength, and nu is your frequency, we should then be able to write out some sort of equation that shows what happens when we multiply them together. So let's start with wavelength. Anybody know what the SI units of length are? This is easy. Meters, exactly. The SI units of length are the meter. Now frequency, we talk about the frequency of something. That means how rapid something happens. It's always measured of something per unit of time. Something per unit of time. So since we don't know what that something is, then we can just always talk about it as being per unit of time. So if it's per unit of time, time is measured in which units? Seconds. But if this is per unit of time, then where does that seconds appear? Inverse seconds, exactly. They appear in the denominator. And so the units of frequency are what we call reciprocal seconds. Now if we go ahead and take the wavelength and multiply by the frequency, let's see, meters, multiply it by the frequency, what is this going to give us for units? This would be meters per second. And what do meters per second measure?
Speed.
Speed, exactly. So a speed of a wave may be found by multiplying together the wavelength and the frequency. And then if we go to light, we say that that speed is equal to c, which is lambda times nu, where c stands for speed of light. Now it's kind of a poor label because it's not only the speed of light, but it's the speed of all electromagnetic radiation. It's the speed of radio waves, it's the speed of gamma radiation, it's the speed of infrared radiation. It's basically the speed of all forms of electromagnetic radiation in a vacuum. Now, you do not need to memorize this value, so if you have your periodic table and conversion sheet handy, on the back side of your periodic table and conversion sheet, you're going to find the speed of light right here. So it's not a to memorize value. You'll find it on the back side of your conversion sheet. And C has a value of 2.998 times 10 to the 8th meters per second. And again, we've labeled the other variables in here. So as far as the units of reciprocal seconds go, a reciprocal second you'll sometimes see written like this, /second, because it's something per second. So these two represent the same thing. But scientists have also come up with another name for this. It's called the hertz. And we abbreviate it with a capital H and a lowercase z. So if something has a frequency of 1 hertz, What this means is that one of something is occurring per second. So a frequency of 1 hertz means one of something, whatever the event is, per second. If it's a wave, what this would mean is that one wave is going to pass for every second. So any questions on this piece here? Okay, let's go ahead and do one of these problems out of the packet here. Let's say we want to calculate the wavelength of a radio wave that has a frequency of 101.3 megahertz. I know some of you have heard of this frequency before. There you go, KDWB operates on this frequency, 101.3 megahertz. So let's see what sort of waves KDWB is putting out. We'd like to calculate the wavelength of a radio wave has a frequency of 101.3 megahertz. Now, some units that you should be familiar with in here would be associated with these prefixes. They are the prefixes micro, nano, and pico. When I say be familiar with, I'm pretty sure that the ACS standard exam that you'll be taking, you'll need to know these prefixes. So we're going to do a quick review here. Prefix micro means 10 to the -6, or 1/1,000,000th. The prefix nano means 10 to the -9th, which is 1/1,000,000,000th. The prefix pico means 10 to the -12th, which is 1/1,000,000,000,000th. And then over here, we will be working with frequencies in these units. You might see something like a kilohertz. You might see megahertz like we're showing on this one. Or if we're talking about spectrum, say of your Wi-Fi at home, it's measured in units called gigahertz. And so we can look at 1 kilohertz, 1 megahertz, and 1 gigahertz. The prefix kilo means 1,000, which is 10 to the 3rd. Mega means 10 to the 6th, which is 1,000,000. And giga means 10 to the 9th, which is 1,000,000,000. Okay, so these are some of the things that we should see. I think you should be familiar with these prefixes, especially when dealing with electromagnetic radiation. So now, if we want to calculate the wavelength of a radio wave that has a frequency of 101.3 megahertz, we then look at our formula, which says C is equal to lambda nu. Now, which of these variables are we going to solve for? What are we trying to find in this one? Wavelength. So if we're trying to find the wavelength, that means we're solving for lambda. Solve for lambda, we have to divide each side by nu. And if you don't like saying that word, just say frequency, all right? Nu is going to cancel out. It says that we will find it by taking the speed of light and dividing it by the frequency, nu. Well, C will never change unless we're not in a vacuum. C is going to be equal to 2.998 times 10 to the 8th. Which page do I have it on? Here we go. 2.998 times 10 to the 8th. This is meters per second. Then we want to divide this by nu, which is 101.3 megahertz. Okay. Well, now we're not going to do a very good job of canceling units here, are we? So now we need to make sure that we get to a point where we can cancel out units. Remember that the prefix mega stands for how much? 10 to the 6. So we can change this times 10 to the 6 hertz. So again, we replace mega with 10 to the 6. Units still aren't canceling until we remember that a hertz is the same as a Reciprocal second. So if we get rid of this here and we replace it with the reciprocal seconds, like this, we should now see that these reciprocal seconds are going to cancel out. They cancel out. That's going to leave us with units of meters. Is meters a unit of length? It is. That's good. So let's go ahead and calculate this out. And we should be able to calculate it just like we see it here on our calculators. So if I were to put this in here, I'm going to go ahead and show you how I put this on my calculator. I'll put it in as 2.998 E8. And then we are going to divide this by 101.3 E6. And so by putting it in like this on my calculator, I then press enter. Looks like we wind up with an answer 2.9595, etc. How many significant figures should be in that answer? 4. So rounding it off to 4 significant figures, we'd write that as 2.960. 2.960. The label on this is going to be meters. And that then would be the result. Any questions on this problem here? Okay, let's go ahead.
Power. So like 102.1 would have more power than 101.3?
102.1.
Because
It's just a longer wavelength, right?
Yeah, if you put 102 in here, then your wavelength is going to go
It's shorter.
shorter.
so it would be less powerful.
In terms of energy, yes, because the greater the frequency, the greater the energy. Yes. Anybody else? Okay, let's go back now to our, I know we're jumping back and forth a bit here. Now let's go back to what this means. If we said energy is proportional to the frequency. If energy is proportional to the frequency, what that means is that if we go back to our original diagram, which is this one right here, we said that this side was low energy, that side over there was high energy. High energy means that the frequency on this side is going to be high as well. Remember that high energy corresponds to high frequency because they're proportional. But what does that do to the wavelength? Shortens the wavelength. So as we increase the frequency, we decrease the wavelength. And what would the relationship then be between frequency and wavelength?
Inversely.
It's an inverse proportion. And you can get the inverse proportion by looking at this particular equation right here. This represents an inverse proportion. If frequency goes up, because this is a constant, that must mean that the wavelength will go down. So again, frequency and the wavelength have an inverse proportion in their relation. So what we'd like to do on, we need our formula here first of all. Because they're a direct proportion, turns out that they form a very nice equation. We say E is equal to h nu. H here is a value called Planck's constant. And Planck's constant has a value of 6.626 times 10 to the negative 34th. Now, I'm not going to give the units to you yet. Let's figure out what those units would be. So now if we're going to figure out the units, let's remind ourselves, what are the units on E? These are joules. What are the units on frequency? Inverse seconds. So now if we want to multiply something by inverse seconds to get joules, that must mean that one of the units in there must be joules. The other must be seconds. And so we call those a joule second. And we see it's a joule second. The units here, seconds and reciprocal seconds, cancel out. Which must mean then that the units on Planck's constant are these joule seconds. You go to your conversions, you're going to see Planck's constant given here. And we don't read it as joules per second because the seconds are not in the denominator. We refer to them as joule seconds. So Planck's constant is 6.626 times 10 to the negative 34th joule seconds. So now we come back to our problem here, and looking at the clock, I think we'll just do this last one for more practice. We'd like to figure out the energy required to dislodge electrons from sodium metal via the photoelectric effect. We'd like to know what wavelength in nanometers of light has sufficient energy per photon to take electrons out from the surface of sodium. All right, so now we look at our formula here, which says that E is equal to h nu. And when we see this formula right here, this formula is representing what the energy is of a photon. So again, this is representing the energy of a photon for a single photon of energy.
Yeah.
So again, for a single photon of energy, that's what this shows. But of course, in our problem, we're not looking for a single photon here. We are given information for a mole of photons, or a mole of electrons that those photons will kick out. So what we need to do then is we need to figure out the amount of energy for every one electron, or for every one photon that's going to get kicked out of here. So we'll start with the 275 kilojoules per mole. And it looks like if we're going to use this formula, our energies have to be converted to units of joules. So we'll need to convert the kilojoules to joules. So to convert kilojoules to joules, up here we're going to put 1,000. Down below we'd put 1. Kilojoules are going to cancel. This is now the joules per mole. If we now want the joules for every one photon or one electron that it's going to kick out, we could say that for every one mole, we have how much? 6.022 times 10 to the 23rd. And again, if we're talking about electrons, right now we're talking about, it doesn't really matter if it's electrons or photons we're talking about. Let's say it's per electron. So there's 1 mole of electrons. This is going to cancel out here and here. And so this will be the number of joules to kick out per electron. So if we go across and calculate this, we'll take 275, multiply it by 1,000. We'll divide that result by Avogadro's number. We wind up with 4.567 times 10 to the negative 19 joules for every one electron. And the fact that it's per every electron or per photon doesn't really matter, because again, each electron is going to be kicked out by one photon. What's more important is what this number of joules is right here. So then we come back to our equation, which says E is equal to h nu. And we look at the one that we've already had, which says C is equal to lambda nu. Because what we're ultimately trying to calculate in this problem is a wavelength in units of nanometers. Right now, wavelength does not appear in this formula, so we need to get wavelength into here. To get wavelength into here, we need to take this equation right here and rearrange it. To rearrange it, we're going to solve for nu. To solve for nu, we divide each side by lambda. Lambda goes away, and now we can make a substitution in here for nu. And what we're going to substitute in for nu is C over lambda. which again tells us E is equal to hc over lambda. So again, we made a substitution. And for nu, we simply placed in c over lambda in right here in its place with hc over lambda. Now we're in a good position because we know what the energy is. That energy is right here. We know what h is because h is a constant. We know what c is because c is a constant. The only thing we don't know is the wavelength. So my recommendation always is to solve for the variable first. The variable here is on the bottom. We want to get it on the top. So to get it on the top, we're going to multiply each side by lambda, and then we're going to divide each side by E. We do that, lambda goes away here, E goes away here, and we find out that lambda is equal to hc over E. Well, now we can substitute in our values. Planck's constant is 6.626 times 10 to the negative 34th. Joule seconds. C is 2.998 times 10 to the 8th meters per second. We divide this all by E, which in this case is 4.567 times 10 to the negative 19th joules. And remember, this is joules for every 1 electron. So now if we look at our units, hopefully we're in good shape. Joules cancel with joules, seconds with seconds. We're left with the units of meters. So now if we run this through our calculators, we'll take Planck's constant, which is 6.626 E negative 34, multiply it by 2.998 E 8. We'll divide that by our previous answer, which is 4.567 times 10 to the negative 19th. And we get a result of 4.35. Now we should probably look at significant figures. Haven't been paying attention to that yet. How many were right here? 3. So if there's 3 there, that means that this answer here should have 3, which means that this number here should have 3, which means we should round this final answer off to 3 significant figures. So it'll be 4.35 times 10 to the negative 7th. The label is meters. We, however, did not want this in units of meters. We wanted this one in nanometers. So we come back to our conversions in case we haven't learned them yet. We're going to come back and look at them here just to remind us. 1 nanometer is 10 to the negative 9th meters. So coming back here, 1 nanometer is 10 to the negative 9th meters. These are going to cancel out. We have 10 to the negative 7th over 10 to the negative 9th. Remember, when we divide exponents, we will subtract. So we take negative 7 minus a negative 9, which is going to give us a positive 2. And so this will give us 4.35 times 10 to the 2nd nanometers, which we probably could write out in its standard form here, because times 10 to the 2nd actually means we move this over 2 places. We get 435 nanometers. And it turns that very often when we look at electromagnetic radiation, we actually don't like to express our wavelengths with scientific notation. Rather, what we do is we change the prefix. So we talk about them in picometers, micrometers, and nanometers. Any questions? All right. If you didn't get your test, I do have them up front here.